So the third and final part of this example is going to do a couple things. The first thing we're going to do is I'm going to talk about how we can use a Spliterator with our sequential stream implementation. And this is a much cooler Spliterator than the ones we've looked at before because it uses regular expressions in a much more powerful way. So we'll talk about how the Spliterator is used to break the input up into chunks for analysis. And we're also going to kind of summarize the pros and cons of the sequential streams implementation. And the reason for doing that is when we start talking about parallel streams, which we'll probably get to probably next week, this will motivate why we care about parallel streams, which are very similar to sequential streams, but way cooler. OK, so what we're going to do here is I'm going to show you how to implement a Spliterator that can be used to look for each of the phrases in the input string, in an input string, right? You can look for phrases in a work of Shakespeare, for example. And the particular Spliterator we're going to look at here works for both sequential and parallel streams. And right now, we're just going to focus on the sequential version, where you're going to have one thing that splits. And then later, next week, we'll start talking about the parallel version that splits things up in parallel. Does anybody understand the reference here about sequential and parallel splitting? The Sorcerer's Apprentice, exactly. And anybody who's ever seen the classic 1940s Disney movie Fantasia, which is an awesome piece of animation way before they had computers, by the way. It was all hand-drawn, if you can believe that. In the movie, they have Mickey Mouse, who's basically the grad student, and his advisor, who's basically the wizard, the sorcerer, sends him off to do this sort of mindless task, right? And his mindless task involves carrying water from a well and dumping it somewhere. And so because he's a clever grad student, he decides to enchant a broom to do this. So it starts out with one broom to do the work. And so the broom does the work. But then he wants the broom to stop doing the work. So he thinks he's clever, and he basically sends a kill signal to the broom. But unfortunately, he chops the broom up into little pieces. That's the Spliterator part. And so then all of a sudden, they have all these brooms that are doing things in parallel. And fortunately, his advisor comes back at the last second and saves him from drowning. But it's a classic example of how sometimes it's easy to start things in motion, but very difficult to shut them down. And it's also a good metaphor for splitting stuff up. So poor Mickey splits the broom in pieces with his axe. OK, so the particular method we're going to look at here that uses our Spliterator is called searchForPhrase. And you can see searchForPhrase is used here in the processInput method. And processInput takes each phrase, turns the list of phrases into a stream of phrases, and it then calls map, and it searches for each phrase. So for each phrase that we have, it'll go ahead and search for it. And we'll see what searchForPhrase does in a second. What searchForPhrase is going to do is it's going to return a SearchResults object. And as we'll see here in a second, that SearchResults object has some pretty cool stuff in it. In particular, the SearchResults object that gets returned here is going to include the title, or actually the input string that we're searching, the phrase we're looking for, the title of the phrase, and then it's also going to have a list of results which indicate the indice where the phrase is found in the input string, if it is found at all. Of course, there may be no matches, so in that case, it'll be 0. So if you look in Julius Caesar for the phrase, neither a borrower nor a lender be, you won't find it in Julius Caesar because it's not there. It's in Hamlet. So of course, the search results will be 0, be empty. But if there is something to find, what happens here is we're going to use our streamSupport.stream method. Remember, this is the method that takes a Spliterator and turns the results of splitting into a stream. So we're going to create a stream, and the stream is going to use this thing called PhraseMatchSpliterator, which we're about to look at in a second. And the PhraseMatchSpliterator takes the input string we're searching and the phrase we're looking for in that input string, and it goes ahead and makes a stream of things that match. And we'll see in a second that it's doing it sequentially for reasons I'll talk about. And then what it's going to do is this stream that comes back will be collected into a list, and that'll be tucked in as the final parameter in the search results object. So search results will end up with the input, the phrase, the title, and a list of any places where matches occur. You'll notice that there's a parameter here called parallel, which is a Boolean. And for this particular implementation, we're going to call searchForPhrase with a false flag for the Boolean, thereby indicating to the streamSupport.stream helper method that we want to create a sequential stream. So parallel will be false. Later, when we talk about parallel streams, you'll see that all we have to do is replace the false with a true, and all of a sudden, this splitterator will be run in parallel. Yes? If you were running this on a sequential stream, do you really need, well, so that kind of, do you need to use a splitterator? That begs the question, when you say running it on a sequential stream. So how did you get that sequential stream? So we need to, if we're going to have a stream, then we have to create it somehow. And so the easiest way to take something and, well, not the easiest, one way to create something that's a stream is to use a splitterator to do that. So in this particular case, we have two pieces of information. We have the input string that we want to search, and we have the phrase that we want to look at. And over time, there'll be lots of phrases, but at any given point in time, there'll be a given phrase. And so we want to be able to create a stream of all the places in the input string where the phrase occurred. And so the way to do that is to use a splitterator to go search the input string to try to find matching phrases, and then create a stream of all the places where the matches occur. So that's the way to do this. Maybe your question is, are there other ways to do it? Of course there's other ways to do it, but if we're trying to use streams, then we need to use a splitterator to go search that input string and break it up into chunks. And perhaps even more importantly, the purpose of this is to explain how to use a splitterator. So whether or not there are other ways to do it, the point of this is to show how to use a splitterator to do this kind of stuff. Okay, so just to recall how this is all fitting into the larger control flow of the program, we've got an input string, Hamlet, all the text for Hamlet. We've got a bunch of phrases, some of which may be in Hamlet, some of which maybe not. We turn those phrases into a stream. We call map on that stream of phrases, and we call searchForPhrase with a false for the parameter here, the one that's called parallel. So it'll be false, because we're not doing it in parallel, we're doing it sequentially. Okay, and then that will return a stream of search results, and as you can see here, which I'm not going to focus on because we've already discussed this before, anytime you search a work of Shakespeare and there's no match, like again, you look for, to thine own self be true and Caesar, it'll come back with the result of 0, so we'll just filter that out so it doesn't consume any more processing resources henceforth. Okay, so this is an example. Let's say we've got the text of Hamlet, just for sake of argument, and it's got lots of famous quotes, and one of them might be the one we're looking for. Brevity is the soul of wit. So there's the phrase we're looking for. There's one of the phrases we're looking for. And so brevity of the soul of wit matches at some place, some index from the beginning of Hamlet, and that's where it starts, right there. So, that's the input of the PhraseMatchSpliterator would be a work of Shakespeare, and the output would be all the places where the match occurred. So how do we do this? Well, we implement a PhraseMatchSpliterator. Now, what I'll do right now is just talk about the sequential version. The parallel version is way, way, way cooler, but we won't be able to talk about that until we talk about parallel streams later. So what PhraseMatchSpliterator does is it uses a Java regular expression instance and a pattern matcher to create a stream of search result objects that match the number of times a phrase appears in an input string. So PhraseMatchSpliterator implements the Spliterator interface. You can find the code here. Spliterator is an interface that's defined in Java, and it's parameterized by what it is you're splitting into. So we're going to split the phrase match, we're going to split the stream into a stream of results. We'll look at result. Result just keeps track of where the thing occurred, like what the index was and some metadata. And Spliterator is an interface that has 8 methods. We're going to talk about just one of them right now called try_advance, but there's a whole bunch of other ones that we'll talk about later. If you take a look at the fields that are part of the PhraseMatchSpliterator, this keeps track of what we're trying to do and how we're trying to split. So the other thing that's interesting about this is these fields are used for both the sequential version and for the parallel version. I'll focus on the sequential version right now, but be aware the parallel version also uses these fields as well. So the first field we have up here is minput, which is a char sequence, and that's just the string that we're looking at. And I use a char sequence because I want to be able to do subsequences of this input string. I want to be able to split it in parallel streams without paying the cost of copying. So char sequence will let you do that, whereas string copies the contents when you do a substring, so it's much more expensive. So that's why we use a char sequence. We then have the phrase we're looking for. We just stash that away so we can use it later. That's just a string. We have a pattern and a matcher. This is used to store a regular expression. This is to take that regular expression, and matcher is used to take that regular expression and connect it with an input sequence or string. In this case, it's the input sequence. And then we also have some other fields like mSplitSize and mOffset. These are used for parallel streams, and I won't talk about them too much at the moment. Here is the constructor for PhraseMatchSpliterator, and this is just a little snippet of it. If you really want your mind to explode, take a look at the actual implementation, because it's got way cool regular expressions. What we do is we take the phrase we're looking for, right? The phrase could be, again, something like, whoops, brevity is the soul of wit, or whatever. It's a string with a bunch of words in it, separated by non-word characters. And what we do is we go ahead and turn it into a regular expression. And we do that by stripping off the leading and trailing spaces. And then we replace all sequences of multiple spaces with a single space. And we also break things up into words. So we have a regular expression that's matching on the words. And I won't even begin to go into explaining all the different things. This is just crazy regular expression stuff. We take that regular expression for the phrase, and then we compile that string into a pattern, which is going to be this pattern. That's a Java 8, or it's a Java type that stores regular expressions. And we say compile this regular expression in a case-insensitive way, so we don't care about capital letters at all, and also do it in such a way where it'll span across line breaks. So that's yet another cool thing. So we end up with a regular expression compiled. And then we take that regular expression and we connect it with the input. So we now have a pattern matcher that will look for this regular expression in that input string. And I'll show you in a second how it actually gets used. Hopefully you have covered regular expressions, or hopefully you will cover regular expressions somewhere while you're an undergrad at Vanderbilt. They're really cool, and they let you do pattern matching, essentially. And then there's some other stuff down here about splitting up the input strings and stuff. That's for parallel streams. We don't worry about that right now. OK. The one method that we do care about is called try_advance. And this is a method that's called by the streams framework. In particular, it's called by the streamSupport.stream method when we give it an instance of a spliterator. It'll go ahead and create the spliterator and then go through the input calling try_advance, trying to find all the places where a match occurs. And so try_advance is going to be called by the framework. And this method essentially plays the role of hasNext and next. So if you recall the Java iterator interface, we have hasNext and next. And try_advance combines them into a single method. So remember, hasNext returns true if there is something else that you can iterate over, and then next gives you back the next item. And it's always been a little wacky why there are two methods. So try_advance says, yeah, that is a little wacky. Let's go ahead and return a Boolean to say whether we succeeded or not, and we'll give the result of a match, of a successful iteration through a consumer parameter. So consumer, if you recall, is that functional interface you can use to accept something into an object. So we use the consumer to pass the result, if there is one, by reference. So we can make changes to this action parameter, as we will do here if we find a match, and that'll then be used to return the result back to the caller, to the streams framework, by reference, because it's going to have a side effect on the object reference that's passed in. So what do we do? We say, hey, pattern matcher, please see if there's any remaining matches, or if there are any matches, or please find me the next match in the input string for the pattern I told you about earlier. Remember the pattern? This was the pattern that we had. So if you got the pattern, I put it with a matcher. This call here says, whoops, please go and see if there are any other matches in that input. If there are no more matches, either because we've already found them all or because there were none in the first place, in that case, find returns false. In that case, we invert it. So if it's, if it returns false, then we're going to go ahead and return the false field from try advance, which is an indication to the streams framework, this stream is done. There's nothing more to match. Otherwise, what we do is we go ahead and, if there is a match, in other words, if we found a matching phrase in the input string, we go ahead and say, hey, phrase matcher, please tell me the starting index where that phrase began. And that'll just return to you the number, which is basically what we saw earlier. If you go back a bit, way back here, it would be, where did it go? It's this thing here. It's the 54739 or whatever, right? Whatever the index is where the match occurred. So wherever that match happens to occur, we are going to go ahead and create a new result object that keeps track of where the match occurred. And then we accept that into the consumer action. And therefore, the streams framework will be able to get that value when try advance returns true. So if we got a match, we update the action with whatever we need to, and we return true, indicating that we got something. So that also, not only will the streams framework say, oh, thank you very much, I'll take a look at that value and stash it off somewhere as part of this stream I'm building for you. And it'll also say, well, since you returned true, I'll give it another shot, right? I'll try to call try advance again. Okay, any questions about what's going on here? So the streams framework under the hood is basically calling this try advance method repeatedly until it gets back false. Now, of course, it could get back false right away, in which case it won't do anything. It'll be an empty stream. But that's essentially how the try advance method gets used. Try advance is what's called for a sequential stream. If you have a sequential stream, if you create the, if you say stream support.stream Spliterator false, only try advance is called. And try split is ignored. However, if you have a parallel stream, then the try split method will be called. And try split, as the name perhaps suggests, is used to take a big input source, like, the text for Hamlet, and then split it up into smaller chunks that can then be handed to the fork join pool, and then you can go ahead and search those things in parallel. So those searches take place in parallel relative to each other. So that's what try split is used to partition the input into many smaller chunks that can run in parallel using try advance on each of the chunks that are left over. So try advance is called when the chunks get to a certain small size, but all those different calls can run in parallel. And we'll talk more about that when we talk about parallel streams. So we're not going to talk about that right now. But that's the other piece of this. Remember, splitterators do two things. They iterate and they split. So they're splitterators. Okay, so let's also talk about the pros and cons. Now that we've looked at this entire sequential implementation, let's kind of evaluate it. So there's a number of benefits with using sequential streams for what we're trying to do here. One of them is the fact that streams use internal iterators, and that's just the nature of the way a stream works, versus external iterators that are used by more traditional Java collections. You've probably worked with these already. If you have an iterator, if you use the iterator object as you have done in your assignment, you have to make an iterator, and it iterates externally over the collection. Likewise, if you use a Java for each loop, which is basically doing the same sort of thing, it's iterating over the elements. And streams use internal iterators versus external iterators. I will talk more about internal versus external iterators later. But the long and the short of it is that by doing this, you can have this really cool, very simple code where the iteration is implicit. You don't know what's happening, and as a result, it gives lots of opportunities for optimization and also shields you from all the internal details of how the stream works under the hood. So you are shielded from the knowledge of how the stream actually works. So it makes your code a lot more concise. You'll also notice that this pipeline that we have here is declarative. So we're not saying how to do it, we're saying what do you want to have done. And that's because we're just applying a bunch of transformations and filtering operations using the aggregate operations terminated with a terminal operation. And that is significant because it allows us to focus on the what, not the how. And why is that good? Because it allows you to say, what is my computation? What do I want my computation to be? Not how do I want to have my computation implemented. Were we to write this in more traditional ways, we'd be doing an awful lot of the control flow ourselves with for loops and if statements and all kinds of other stuff. And that just kind of totally goes away using a stream, and you just focus on what you want to do rather than how it's done. Obviously, the streams framework focuses on the how, right? It's doing all that stuff, and it's figuring out how to pipeline these things together, and if it's doing it in parallel, it's figuring out how to parallelize it and so on and so forth, but this is nice and clean and declarative. Another thing that's nice about the way that you use streams, if you do them correctly, of course, is that you write lambda expressions or method references that have no side effects. So if you take a look here, everything is self-contained. SearchForPhrase takes these parameters, and it returns a search result object. This particular filter method reference just gets rid of stuff that's empty, right? And these things have no side effects other than to return a value. And not having side effects makes it a lot easier to reason about your program behavior, because you don't have to really dig under the hood. You have to know what SearchForPhrase does. You have to know what SearchResults is empty does, but you don't have to know any side effects it may have, because it's only returning values through the output parameters. And so not only is it more easy to reason about your program, it's also able to optimize it. And we'll talk later when we talk about how streams work under the hood, how optimizations are done automatically for you by the streams framework, which is really cool. Of course, not everything is rainbows and unicorns, so there are some downsides with using sequential streams. And the most obvious downside of using sequential streams is that it can't take advantage of multi-core processors. So as we've talked about several times in class, especially at the very beginning, the world is headed in the multi-core direction. My current laptops have hyper-threaded quad-core processors, and I got them about a year ago. I was out looking for a new laptop for a variety of reasons just the other day, and I found that a year later, they now have the same configuration comes with 6-core hyper-threaded processors. So in a span of a year, it used to be you wait a year, year and a half, 2 years, and everything got twice as fast. Well, that's not happening anymore, but you wait a couple years now and you got more cores. And I wouldn't be the least bit surprised in another year if they came with 8 cores out of the box, right? So each new generation of hardware for a certain class of machine just gets more and more and more cores. But sadly, this particular implementation isn't going to be able to leverage that because it's only running one thing at a time. Isn't that too bad? And obviously we're going to fix that when we do parallel streams, right? So that problem will not remain a problem for long. But the consequence of that is something you can actually see quite visibly here. This is showing the performance results for the different implementations we'll look through. We'll look through some of these, not all of them. But here's poor sequential stream all the way at the bottom. And look at the really high-end ones. They're way, way, way faster. 400 milliseconds versus almost 2,000 milliseconds. Boom. much better. And when we look at the implementation of this version versus that one, you'll see that it's almost identical. It just changes, sequential to parallel, and everything else stays the same. So you can get these huge speed-up boosts on a parallel machine with minor changes to your code. That's what it's all about. This example also, while being very simple to understand, also only uses a handful of stream operations. There's lots more. The good news is, even though we only use a handful of them, they're all relevant for parallel streams. So when we talk about parallel stream version, you'll see that the only thing we do here really is we change stream to parallel stream. And all these other operations work perfectly out of the box. So that's where we're headed down the road. There are lots and lots and lots of other aggregate operations. And I forget whether it was Olivia or someone else had asked earlier, how do you know what they are, right? And so the way you know is you go look at the stream class here. It's actually an interface. And it'll tell you all the things that you have available for you. Yeah. Oh, it's a con for my example. It only shows a few things. So, but don't despair. We will talk about other cool things later. We'll show more of these operations later when we talk about another example. There's a thing we'll talk later called the parallel image stream gang example, and we'll look at a lot of other cool stuff in that space. So you'll get more exposure. The point is you get more exposure as we go along. Okay, so that is the end of the sequential search stream example, part 3.